Hey y'all, I'm Matt Butcher. I'm the CEO of Fermyon Technologies. We're building the next wave of cloud computing with WebAssembly. I'm kind of a PowerPoint person, like the other developers at Fermyon jokingly refer to PowerPoint as my IDE of choice. So I'm going way out of my comfort zone today, and I'm going to stick to VS Code. And we're going to take a look at an application built using Spin, deployed locally, deployed in Docker Desktop, and then deployed into the cloud. And we're going to use some of the LLM stuff that you probably heard about a little at the keynotes today to be able to build kind of a fun little application. So like I said, I'm going to try and keep this mainly in VS Code. So I'm using this program called MARP that I've never used before that converts Markdown files to slides. Show a couple of slides to give you sort of an overview of what we're talking about, and then we'll get into some code and look at it. We're going to look at TypeScript code, but we're not going to do anything terribly intense. So even if you're brand new to programming or don't really write much code, this should be fairly straightforward to follow. So with that, let's get going. So WebAssembly, Spin, AI, and Docker Desktop are a whole bunch of buzzwords kind of all crammed into one title, but don't worry, we'll make it through all of these, and it's not going to be terribly intense. I do want to kind of introduce WebAssembly to you, though, if WebAssembly is a new topic. There are a whole bunch of sessions today on WebAssembly, and I'd encourage you to go to some of the others to get a feel for what the different things are that are happening in the WebAssembly ecosystem. But essentially, WebAssembly was designed to be an operating system and architecture neutral binary format, the kind of thing that you compile your programs to. And the idea originally in the browser was that you could run other languages side by side with JavaScript. So for example, if you had that crufty old C library that you didn't want to try and rewrite in JavaScript, you could compile that to WebAssembly and then call into and out of that library using JavaScript as a bridge. This is a very cool technology that places like Figma made use of, Adobe makes frequent use of it. And it supports a really broad range of programming languages at this point, including new ones like Rust and Zig and Go, old ones like C and C++, scripting languages like Python, JavaScript, TypeScript, Ruby, and the like. The interesting thing about WebAssembly is that it actually is fairly useful outside of the web browser as well. So at Fermyon, we've been looking at ways to sort of speed up the cloud, and in particular speed up a very specific class of cloud applications. And the easiest way to sort of explain this is to look at how the cloud has evolved. Kind of the first wave of cloud computing was very much oriented around the virtual machine. The virtual machine is awesome, right? It is the heavyweight class of cloud computing. It'll be here for the rest of the, probably till the heat death of the universe, right? It packages up the entire operating system from the kernel and the drivers all the way through all the libraries, the system utilities, and up to your application code. And then you can ship it off and run it on somebody else's hardware without really having to know very much at all about what that hardware looks like. For me, when I first ran into it, this was a fairly profound shift in the way I had thought about operating systems and hardware, because if you rewind to the pre-cloud days, we were always thinking about operating systems as having a one-to-one relationship with the hardware, and now suddenly you can package that whole thing up and run it somewhere else and have no worries that, that the other virtual machines running in that same piece of hardware somewhere can attack yours, can somehow circumvent your security model or anything like that. So virtual machines really enabled all of cloud technology. Probably indisputable. But as a developer, I was never a huge fan of building virtual machines because, well, for two reasons, really. The first one is you're building these massive artifacts, right, that include tons of stuff that I, as a developer, simply didn't care about, right? I didn't want to know all the different pieces of all the different things that needed to be on the system. The second one is I didn't really want to take responsibility for that, right? That was me as a developer taking on a huge amount of operational responsibility about which I was not an expert. So when containers came around, I was very excited because containers gave me the right level of abstraction for the kinds of servers that I was writing. So I was writing microservice-style servers where I would run a long-running process that did JSON over REST, that kind of thing. And a container basically gave me a way to package up just sort of like a pie slice of the operating system. So instead of going from the kernel all the way through all the core libraries and the utility daemons and all that kind of stuff up to my application code, it was really just I packaged up the piece of the file system I needed in a Docker image along with my particular application code, and then I could run these long-running servers for as long as I needed inside of that environment. And I think a lot of us really liked that middleweight class of cloud computing, where we could build applications that way. And using tools like Docker or Docker files, it was so easy to do. But a third kind of cloud computing has gotten increasingly popular. And that's this sort of Lambda serverless function as a service style model, where really what I want to do is not write a long-running server process, but write a small event handler that takes a request, does some stuff, returns a response, and shuts down. Now, if you've used Lambda, you know that each Lambda function has a startup cold start time of between 200 and 500 milliseconds. In many cases, it can take a couple of seconds before your application can even respond when you're writing Lambda functions. And the reason why is because underneath the hood, all of Lambda is actually built on virtual machine technology. And virtual machines were designed to solve a very different problem, and quick startup time is not necessarily one of the original design goals of virtual machines. So consequently, the underpinnings in that cloud layer are, and this is across really all of the current functions as a service models, right? The underpinnings are these older technologies that were designed for long-running processes that we've tried to adapt to run these kind of, nearly instant processes. So if you're familiar with kind of the way Google does page ranking, right? At around 100 milliseconds, Google will start dinging you if you haven't started returning data back to the user. So a 200 to 500 millisecond cold start time means that we're getting dinged by the Google search algorithm before we even return our first byte. So for us, when we were looking at this kind of next wave of cloud computing, we said, okay, we've got to get way underneath that 100 millisecond cold start time. And so we started looking at technologies, and WebAssembly really bubbled up to the top. In fact, at this point, we've been able to get WebAssembly binaries to cold start in around a millisecond. And so you're getting much closer to like native binary startup speed than you are to sort of like the virtual machine or container startup speed, where you're talking minutes or seconds, or hundreds of milliseconds. So there are three big advantages to using WebAssembly in this cloud layer. First one is security. Any cloud service has to be secure, right? You have to protect the cloud provider has to protect your application from being attacked by other applications, and the cloud provider has to protect their control plane from being attacked by the application it hosts. So security is a big deal. WebAssembly has a security model that's actually a little bit stronger than the container security model, because there isn't even unmediated access to the kernel, right? Everything gets mediated through the WebAssembly host runtime, which means you can intercept all the system calls. It's also really fast to start, fairly fast to run. Again, we're talking like 1 millisecond cold startup times, and getting close to near native speed for execution time. And then the last one is this idea that once you compile an application to WebAssembly, you get around one of the problems that we all kind of get a little vexed with when it comes to containers. And that is, you compile it once and you can run it on any architecture. So just about any of the CPU architectures, many of the different GPU architectures, many different operating systems, not just Linux and Windows, but Linux, Windows, Macs, a whole bunch of exotic operating systems. So you really get this kind of write once, run anywhere feel that was kind of originally made popularized by Java, but in a way that actually bears fruit and does so in a very secure way. So those things got us really interested in using WebAssembly to build this kind of cloud runtime. So we built an open source tool called Spin. And Spin makes it very easy to build these applications, makes it very easy to compile them into WebAssembly, makes them easy to deploy in a variety of environments, and it follows that serverless paradigm. And that really is the kind of event thing, where the code you're writing when you write a Spin app is an event handler. It takes a request, does something, returns a response, shuts down. So no long-running servers in that case. All right, so that was the background on WebAssembly and why I'm really enthusiastic about it. Now we're going to go in a different direction. So I have recently found myself getting a little bit maybe addicted to crossword puzzles. This is not a thing that I ever really got into in the past, but then I suddenly started, picked up a book one time and started doing these things, and it was, just now I find it a really delightful way to relax. So if you're familiar with the way like the New York Times does crossword puzzles, on Monday, they give you an easy puzzle. So, I can finish in about 20 minutes, feeling pretty good about myself. Tuesday, it's a little bit harder. Wednesday, it's starting to push my limits on the kinds of knowledge that I have readily available to me. And by Thursday and Friday, I'm swamped, and I've never yet completed a Saturday or Sunday crossword puzzle in the New York Times, right? So it's very interesting in the way that it advances. How do you advance a crossword puzzle, right? How do you make it more advanced? Well, the way is you create clues that are a little more opaque, that require a little more esoteric knowledge, that are maybe a little more open to plays on words or puns or things like that, to force the reader to kind of have to think a little bit harder about what a one-word clue like slow might actually be getting at. So I developed a rather annoying habit, or at least my wife found it very annoying, of asking anybody in the room, hey, who was in the Bourne Identity? Who were the stars of that? I tried Matt Damon and that doesn't fit, right? And everybody who's doing stuff, like my daughter's doing homework or focusing on work or something like that, gets annoyed with me. But on the flip side, I always felt like it was kind of cheating to just go to IMDb and look it up, or go to Wikipedia and look it up. I did that, but I always felt like it was kind of cheating. And I thought what would be really nice is if I had someone who I could just sort of have these conversations with that could kind of prompt me to think a little bit differently about it. What are synonyms for the color blue, right? And it dawned on me, an LLM is not a bad way to do this. We've heard a lot about the AI things today, right, and yesterday. These kind of chatty sort of models are great at parsing information, giving you back some sort of relevant human readable text. And I thought maybe I could train up a model to do this. Fermyon Spin has a Llama 2 model built in, and I thought, all right, this is going to be my project. I'm going to give it a shot. So that's what we're going to kind of walk through as I go back over to the code editor at this point. So if you want to take a picture of this, I'm not going to put the slide back up, but I thought I'd give you a moment. If you want to take a picture, this is sort of the getting started stuff. So if at the end of this, you want to go try this out yourself, there are two places you can go. Developer.fermyon.com will get you straight to the developer documentation. Right? You can always go to fermyon.com and make your way in, but developer.fermyon.com is all the open source stuff. Will get you straight into the application building process. And then the demo that I'm giving today is on GitHub at Technosophos, which is my username there, github.com/technosophos/crossword-helper. And actually the slides you just saw are all in there too. So if you need to jog your memory about anything I said, all that information should sort of be in the same place. All right, with that, I'm gonna exit out of this slide presentation and we're gonna start looking at some code. So again, keep in mind we got this crossword puzzle here that we're using, and we want to build a solver for this. So I've already built the code for this, and I'm going to show you the code right up front so that you can see what it is that we're trying to do. So I'm going to do a spin up. So again, I've already built a binary. I'm just going to deploy it locally. We're going to take a look at the UI. Then we're going to go back and look at the code and sort of see what's going on underneath the hood. So spin up is starting in a couple of seconds. I've got localhost port 3000 running. I had preloaded it because I wanted to make sure this worked before standing on stage. But here's the application that we built. Very, very simple. There's a text box here where I can ask a question, and then I can click the Get a Hint button. So let's try that Bourne Identity question. Who were the top, 5 actors in the movie? So again, I'm asking identity. Again, I'm asking it to give me some hints, right? So that I can look at this and say, okay, do any of these fit into this clue that's, star in Bourne Identity? And so I can run that, and then it's going to send that off to the LLM, and it's going to give me back an answer. So what's going on here is I've got kind of two big things in this application. I've got the front end, I've got the back end. So the front end is just this index.html file. It's a very, very boring index.html file. It has like one little JavaScript function that does the round trip with the question answer stuff, and it's got a couple of buttons and text fields and stuff like that. So not at all a sophisticated front end. Then I've got this back end that's a serverless function that's going to handle the querying of the LLM. And then I've got this spin.toml file. So the spin.toml file is really you can think of it as sort of like a compose file for these kinds of serverless functions if you used Docker Compose before. But really less about stringing together services and more about declaring to the runtime how to route requests in and then start up the WebAssembly modules and then send the data back. So I got a little bit of front matter up here, and then I've got two components. The first one is a crossword helper. That's the code we're going to look at. And notice it's going to load this crossword-helper.wasm file when it executes it. And the second one is a static file server. All that's going to do is serve out that index.html file that we just looked at, right? So that's really pretty much the gist of what the spin.toml file does. It says, hey, this server is running these particular endpoints, and when a request comes in, this is how you route it. So essentially, we're running multiple binaries in one runtime. All right, so let's see what happens when I press that Ask a Question button. It comes into Spin, which recognizes this as being a request for the crossword helper. And so it fires off this serverless function called handle request. So it's going to load and start up the WebAssembly binary, again in under 1 millisecond. And it's going to execute the function called handle request. Again, this is TypeScript. We support a whole bunch of different languages, but TypeScript's sort of like my easy go-to. And so really quickly, all it really does is take a request, do something, and return a response. So it's a very basic function signature in spite of the TypeScript, voluminousness of a definition. So we're going to do just a couple of things. First thing is we're going to grab the question out of the request body. So that's what we do here on line 47. Then we're going to ask the LLM to run an inference for us. That's where we basically pass the question off to Llama 2 and say, hey, give me an answer. We get the answer as the result. And I am seriously just sending back an HTTP response with the full result in it, not doing anything fancy at all with this. So let's look just for a moment at this infer function. And it takes 3 params. So the first one is the model that we're going to use. So if I were writing something that generated code, I might use like the Code Llama model. You've probably heard a lot about ChatGPT 3.5, a whole bunch of other models that are available out there. I'm just using Llama 2 Chat, which is the Llama 2 model optimized for these sort of chatty sort of plain text interactions, human readable interactions, right? So that's my model. I'm going to ask it a question. We're going to look at the ask function in just a second because it's interesting. And then I just pass in a little bit of additional information. I tell it that I kind of want somewhere in the neighborhood of around 150 to 200 words. Tokens are sort of like word chunks. So the max number the max amount I want to get back from this is just kind of a couple hundred words. OK, so let's take a quick peek at the ask function. All this really is a string formatter. You have probably noticed some markup like this in demos you've seen in one of the keynotes today. But essentially what we're doing is we're telling the Llama 2 chat model, this is how I want you to behave. And that's a system directive. And then we're passing on the question. So I'm not a terribly good prompt engineer. So if you were translating this sort of hardness-wise to SQL select statements, I'm basically doing the LLM equivalent of select star from whatever. Right? This is not a terribly sophisticated prompt. You'll see prompts that are like that long and are very detailed. The consequence of this is we might get some really interesting answers today because I haven't been terribly clear on what I expect it to do. But essentially I'm telling it, look, you're helping me solve crossword puzzles. And you're going to try and suggest answers that are around 20-ish characters because a crossword grid kind of maxes out at, I think, 21 or 20 by 21 or something like that. And just give it some really basic instructions on how to do it. I tried some more sophisticated ones. You can even see some of them commented out. But in the end, I thought, this will be kind of a YOLO demo. So that is just formatting the question we get from the user into this one that tells the LLM how we expect it to respond. Then we're going to send it off to the LLM. And we're going to wait for it to give a response. Now you're probably wondering, so why did he show the beginning of the inference and then go over and talk about the code without showing the results? Well, the reason why is because I'm running this locally. And I'm running it on CPU and not GPU. So when you're dealing with a large language model and you're running a system that is not terribly optimized for it, it takes a little bit of time. So while it's been churning away in the background, eating up most of my spare CPU, I've been talking. So here it came back at some point while I was talking and said, here were the top 5 actors. Oh, and this is a great example of the LLM just not getting it, right? In fact, Brad Pitt, Morgan Freeman, Zoe Saldana, James McAvoy, Daniel Craig, none of them were in The Bourne Identity. When I ran this last night, of course, it gave me exactly the cast of The Bourne Identity. But this is a good example of how my prompt engineering probably wasn't exactly great. So I could take another attempt at this, and we'll probably do that in a couple of minutes. But yeah, part of the reason why that answer is likely not very good is, again, because I'm running locally, I didn't want to run the biggest version of the model. I wanted to run really the smallest one that I thought could give me reasonable answers. So locally, I'm running the Llama 7 billion parameter model. And they go up to 13, I think 60, 70 billion is something like the biggest. But when you think about the complexity of the abilities of the AI, the sort of reasonable rule of thumb is the more parameters it supports, approximately the better it does at answering general questions, right? There's all kinds of caveats around that, but at least in terms of Llama, that's a good way to think about it. The 7 billion one is going to give fairly basic answers and sometimes vastly misinterpret the sentences, and whereas the 13 billion one often does a much better version, and I haven't even played with any of the bigger models. I mean, we could talk for a moment about why that works and why CPU is slow and GPU is fast. But I think kind of in a nutshell, I would summarize it by saying our tendency when we think about a machine that talks to us in human language is to assume that it's doing some kind of high-level cogitation. In fact, it is not. It is doing a lot of vector math. And it's calculating distances between the probability that a word will appear in this environment, in this context versus another context, and is basically predicting what a response should look like based on the massive amounts of training data that were ingested in the development of the model. So because of that, and you think about vector math, right? What are the areas where we use vector math in computing? Well, graphics, right? When we're playing Call of Duty, we need a very high performance graphics card, or what used to be a very high performing graphics card. Then along came crypto mining. That also did a lot of similar kinds of math, and so a GPU could be used for that. Now LLMs really sort of amp it up, and so if you're running on a MacBook M1 with the old metal GPU in it, it's going to be fairly slow. If you're running on a cluster of NVIDIA A100, highly AI-tuned, massive GPUs, then you're going to get much faster times, and consequently you can use bigger models. So that's sort of in a nutshell why we're talking about slow on a local one versus much faster when we're running on GPUs. Did anybody see that last part of the keynote today, the web GPU thing? So I wish that I could have gotten my hands on that, because that actually helps solve some of these problems here, and that Docker itself can kind of negotiate what the underlying GPU is. What we'll see today is that Docker cannot do that. So when we run this inside of Docker, we're also going to have to use CPU. But then at the end, we're going to run one on GPU in the cloud and see the difference between these. OK, so we walked through some code. Let's talk about how we build this code. So this is TypeScript. TypeScript is an interpreted language. It's actually usually transcoded over to JavaScript and then interpreted. But what we're going to see here is that we can compile it into a WebAssembly binary. We're going to do a single compile here, and we're going to build the WebAssembly binary. We're going to package it up in a Docker container. We can take a look at the make file here and see how that's going to work. So I'm going to type in make build in a moment. It's going to do a spin build, which builds the WebAssembly object. And we can really, because it's platform neutral, spin build run on Windows or Linux or Mac OS, the artifact it builds is going to be the same. But then after that, we're going to use Docker buildx, and we're going to build out a container image. And we'll come back to that one in just a second and see what this command is. And then at the end, I just put the Docker image ls to sort of debug so I could verify at the end that everything looked right and the sizes looked approximately right and stuff like that. So right now, we're going to go ahead and run that build command. So I'm going to do a make build. It's going to run there. While I'm doing that, here's a peek at what the file system looks like. You can see this target folder here is where the WebAssembly binaries go. We've got two of them. We've got the crossword solver, and we've got a static file server. And then you can see kind of at this root level, I've got the Docker file and some other things. And we'll take a peek at those in a moment. So here's the output of our build command. The first thing it did is run spin build to build my WebAssembly binary. Compiling is kind of boring, but with JavaScript, there's something very interesting going on here. So JavaScript is an interpreted language, like Python. So the way Python would work, or the way JavaScript would work, is the environment would start up an interpreter. The interpreter would load the source code files into it, and then the interpreter would begin executing those files. So typically, if you look at a Node application, you've got this giant Node modules folder that just has all the source code in there, and at startup time, it's loading through all the stuff there. We don't want to do that, right? We want a WebAssembly binary output. So the naive way to do this in WebAssembly would be to simply execute the interpreter and feed in the scripts one at a time, like you'd see with Node.js or something like that. But a really cool thing about WebAssembly is that WebAssembly is a stack-oriented binary format, so really at any point we can freeze the running instance and serialize it back out as an executable WebAssembly binary. So this means you can do something very interesting with a scripting language. You can start the interpreter, you can load all of the scripts, and then you can pause it, snapshot that, and now you have an executable that has all your script files preloaded into it in its executable format, right? And you can skip all the cold start time that you would normally get starting an interpreter and doing all this disk I/O. And the result of it is, you get this binary file it's just a single Wasm artifact, right? Now I can't remember the target. There we go. So this Crossword helper Wasm file is a JavaScript interpreter, all the script files that were generated, all the dependencies that I needed from the node modules, and all of that stuff sort of packaged up in one binary. Really, really cool thing about WebAssembly that I think gives it an edge when it comes to these cold start times. So by the end of that process then, we had those WebAssembly binaries in there. Then we kick off this Docker buildx execution here, right? And Docker, especially the newest version, 24 has got some excellent support for this, can build WebAssembly packages, WebAssembly-based images, and then instruct the runtime on how to execute them. So we have to do a couple of things. The first one is we have to tell it explicitly what the platform is. This isn't ARM Linux or something like that. It's WASI, which is WebAssembly System Interface, which says this is how it interacts with the system, Wasm, right? We turned off provenance because I have not yet figured out how to make all of that tool chain work with Docker, but we'll figure that out. And then we build an image called docker.io/technosophos/ apps gets expanded to Crossword helper latest. So essentially, we take that WebAssembly thing, we run it through the Docker file, and we build a new Docker image. The Docker file is very basic in this case. We're going to start with a scratch image, which if I can, it's the trivial things I can't figure out how to do, like scrolling up. We're going to start with a scratch image. We are going to copy in the spin toml. Remember, we saw that file. It's sort of like the Docker compose of the spin world. And then we're going to copy in our two binaries, the two Wasm files. And then we're going to copy in the assets directory. That basically had that index.html file, so that the static file server is going to serve. It's going to serve anything in the assets directory. If we had CSS or images and I was any better at writing web front ends, we would also have those kinds of files in here. But you get the vanilla index.html with Bootstrap pulled in. And then entry point is just a required field when you're building these images. Conventionally, we give it spin.toml as the entry point, but this is all not dropping into the standard container runtime. This is dropping into a different executor, and that executor is going to ignore this anyway. So really, we put it here because it's required for the image for a Wasm image to build, but it's not actually doing anything. Again, conventionally, we just put spin.toml in there. All right. So it's that buildx command is going to build a scratch image based on this. It's going to have just a couple of files in it. And at that point then, we can run our WebAssembly inside of Docker. So here we'll go back to the make file and we'll look at the Docker run command and just glance at this first -- runtime thing, right? -- runtime is telling Docker desktop, hey, instead of using your regular container executor, load this executor called io.containerd.spin.v1. And that will execute a WebAssembly module instead of a container image. To get this to work, you do have to turn something on in Docker desktop. Because this is an experimental feature. It's in development. Every time there's a new release, we see new stuff added here. So it's very exciting. Jordy from Docker is giving a talk later on. He's the developer who wrote all of this. So if you're really interested in the innards of how this works and how different WebAssembly runtimes are supported, his talk will be great. But for us, to enable this, we go into the settings for Docker Desktop. We go to Features in Development, and we have to check two boxes. The first one is using containerd as the executor. And again, if you want to hear all about how containerd works and how these requests sort of get proxied from the default container runtime to other runtimes, go to Jordy's talk. But for all intents and purposes for us, containerd is necessary to run WebAssembly. And then after that, we check the enable WebAssembly thing. We restart Docker Desktop. And then at the end of that, we suddenly have available to us the runtime io.containerd.spin.v1. So we go to run Docker run. We tell it, hey, we want the spin runtime instead of the container runtime. This is going to be a Wasm module. It's not going to be a container image. Then we get the usual port mapping. And then we got this big long line that I'll come back to in just a second. And then we say, OK, and we're going to run that Docker image that has the Crossword helper. OK, so we'll pause on that for a second. LLMs are big. The 7 billion param Llama 2 model that I'm using is about 3 gig. I don't really want that in my Docker container, particularly because I also want the ability to kind of hot swap in and out with how many parameters I have in there, and partly because I just don't want it in there. It's big. So instead of copying it into the container image, which I could have done in the Docker file with a copy command, instead I'm just volume mounting it. So you can see here I'm volume mounting the Llama 2 7 billion chat artifact, which I downloaded off of Hugging Face. and I'm mounting that to this directory.spin AI models llama2 chat. And you'll notice that I named this thing llama2 chat so that if I swap in and out the 13 billion or the 60 billion param model or whatever, I can just change that volume mount. That's actually all I have to do. Okay, so we got this Docker run command that's going to volume mount that's going to run this inside of Docker desktop using the WebAssembly spin executor, and then we'll be running inside of Docker. Now, just as a quick side note, we didn't recompile anything. So we are going from something that was compiled on macOS natively, and we're going to execute it inside of a Linux environment now without having to recompile anything. So I'm going to do a make run. And we can see it starting up, and I probably, oh no, I didn't forget to shut the other one down, good. So now this is running at the same address that that other one, that my local version was running before. I was afraid there for a moment that I might not have made the change. So now we've got the Crossword helper running again. And we've got it running this time inside of Docker desktop instead of locally, and the only difference was really how we packaged that up. So let's ask another good crossword puzzle question. There are always these synonym-related ones, like, one that I got recently, pink otherwise was the clue, or something like that. And I'm like, I don't know, synonyms of pink maybe. I don't know my colors terribly well. Let's do it as a question. What are 5 synonyms of pink? I didn't use quotes here. Let's see what happens. So again, this is going to take a while. And again, this is because we're running the inference on CPU. This time, we're running all of that through the Docker's infrastructure, right? So even if I had optimized outside and been able to use my Metal GPU outside, up until this morning, there was no way I could optimize it inside of Docker. Now this morning, with this announcement that we have the web GPU coming soon, that'll mean Docker will be able to figure out what the most efficient way to execute my GPU-based workloads is, and I won't have to worry about it. So it'll be a great abstraction. I'm very much looking forward to that. So here it's thinking about what synonyms are for pink. I suppose while it's doing that, I'm going to get a lead on the next part and say, okay, ran it locally. Now I'm running it in Docker desktop. Let's push it out to the cloud where we have a bunch of A100s. So Fermyon Cloud has a bunch of fairly heavy-duty AI-grade GPUs available to it, all on the free tier. So I can actually, deploy this for free. And that's just going to do a spin deploy. It's going to package up that same binary I already built, going to ship it off to Fermyon Cloud. I don't know anything about what I do. I'm pretending to not know anything about the operating system or architecture of any of the runtime nodes there. In reality, it's a very large Nomad. It's a very small Nomad cluster, about 8 nodes, Nomad workers running on Linux, probably ARM right now. I don't know. We switch back and forth depending on whatever is cheapest. And that's one of the advantages of cross-compiling, of binary neutral binary format. Okay, so that's running along there. If we go back to our last example, we can see that at some point in the last minute or so, the Dockerized version of Crossword Helper came back, and actually, that's pretty decent. That's a pretty good list of some synonyms in there that very likely would fit in a crossword puzzle somewhere. So while that was going there, now we've deployed it to Fermyon's cloud. We're going to just open that in a separate window here. And once more, we see the Crossword Helper UI. Again, I'm sorry about that. Let's just run that same inference again. So what was it? What are 5 synonyms for pink? Synonyms. Spelling is obviously not my forte. All right, I'm going to get a hint on that. Right away, I get that back. Actually get a very different version this time, and it's a little more chatty, right? It says, sure thing, here are 5 synonyms for pink. I should have said in the prompt, be really enthusiastic about your answers. Rose blush, coral salmon, fuchsia, right? I don't know if y'all can see that because it's went back to my default font size, but fairly succinct list of synonyms for pink. Again, all of these likely ones that would be in a crossword puzzle. You noticed that it came back, within a couple of seconds. So let's do the Bourne identity one again here. Who are 5 popular actors in the movie The Bourne Identity? Get a hint again. I'm going to wait just a couple of seconds. Again, it's very enthusiastic. This time, it gave me a much better result. Matt Damon was Jason Bourne. Franca Potente was Anna Kallman. I mean, this is a nice example because now I've got some better, crossword clues where I can say, oh, it did say her. Okay, I can go and kind of try and narrow down there. Why is this one doing so much better than the local one? Why is it a little more chatty? Well, because now I'm running the 13 billion model on a very, very high-powered set of GPUs. And so it's faster, but also I can run one that's more sophisticated in its answers. Now, it just so happens that in this case it was very right. Still, even with the 13 billion model, it can be very wrong. And again, that's because at the end of the day, we're not talking to a homunculus that's answering these questions for us. We're talking to a mathematical algorithm that's trying to calculate distances, and sometimes it doesn't do a very good job. But with these 13 billion models, they tend to do better. And then the higher end models, the 60 billion models and stuff like that, again, far more GPU necessary, but oftentimes you'll get yet another boost. And the boost does tend to taper off. So between 7 billion and 13, you see a huge jump in accuracy. After that, you get smaller and smaller jumps in accuracy, or at least that's been my experience. This is a minor miracle in that we got through all the demos without anything breaking seriously. But let's talk about what we just did, and then I'll open it up for some questions. So again, sort of the goal here was to take a look at WebAssembly as a technology, right? Something that plays a role outside the browser and provides us this cool environment to write these very snappy serverless functions. From there, we looked at how we can use LLM inside of this kind of environment. There are other things we didn't talk about, right? You can also use databases, you can use key value store, all kind of the basic sort of things, your usual file system, interop, and there are secure ways of using all of these things within WebAssembly. But the LLM thing is new and exciting. I'm really passionate about it. I'm very new to actually writing code using LLMs, but my gut feel about this is that just like if you went, so I started programming in the 90s, right? Back then, I was not allowed to write SQL as a full stack developer. I had a DBA who wrote SQL. And I would say to the DBA, hey, I need you to select me these things out of this table and give it, and the DBA wrote that and gave me back a stored procedure which I was allowed to call for my code. The idea was the DBA was an expert in database systems, and I was a mere full stack developer. Of course, that went away, right? Pretty much all of us have to know some degree of SQL now to get along, and even an intermediate full stack developer tends to know the difference between using an inner and an outer join, or how to do an insert and an update and all of those kinds of things. And the DBAs really, where there still are some, are very highly focused on large installations, specialized databases, and things like that, right? So you saw the narrowing of scope of the DBA into highly specialized stuff, and the broadening of scope for the full stack developer to encompass SQL. I played with this for about 5 minutes and went, oh my gosh, every full stack developer is going to need to learn how to do prompt engineering, and we're all going to love this because we can do cool applications like this in 50 lines of code. So I'm very excited about that, and that's why I wanted to show that particular bit today, because I think this is going to become the new normal for us within the next year or two. And then so from there, then we looked at how we could package it. We could run it locally, we could run it inside of Docker, we could run it inside of Fermyon Cloud. We saw how one binary format really just ran in all 3 different environments. I'm really excited about being able to do this in Docker because it means we can deploy and sign and verify and all of that using all of the Docker ecosystem. We can store these things in OCI registries like Docker Hub, and it's just a very easy way to work with tools we're already comfortable with to build and deploy this brand new WebAssembly serverless function style thing. And then we kind of looked at the end at running this on Fermyon Cloud, where the major salient difference there is how big of a change it makes when you're running these things on small CPUs or on small GPUs versus these kind of AI grade GPUs. And with today's announcement, I had no idea they were going to announce this today, but it's like just perfect timing, because now you can see what's coming and why it was a big deal when they put up those that and one more thing this morning, that we're going to be able to get increasing performance inside of Docker environments that, again, abstract away from the actual details of the hardware, which is one of the things we really love about Docker. So with that, I think I've got about 5 minutes-ish for questions. I have to put my headset on here, but if you've got some questions, I'm happy to answer. Otherwise, we can all just work some crossword puzzles.
What's been your experience with...
Hold on.
OK, sorry. Wait.
Where's the volume knob?
Just yelling in your ear.
There we go.
How about now?
Oh, that's better. That's better.
What's been your experience with the performance of WebAssembly? I've done some tests and I've seen like there's these claims of near native performance, and I'll like create a Rust server and then I'll compare it to the WebAssembly server, and it's not even close.
That is a great question because it's something I kind of glossed over here, but it's a very interesting ecosystem. So WebAssembly can run in 3 modes. It can run in pure interpreted mode, where it reads the bytecodes and executes them as it goes. This is a brilliant way of running something when you're in a memory-constrained environment, or when you're in a small, when your device really doesn't have the ability to process information that quickly or cache a lot of stuff. Java is the same way, right? You can run Java in a pure interpreted format, but most people who run Java use what's called a JIT, a just-in-time compiler, that'll compile it as it loads it so that it can run a little bit faster. Java, the Java ecosystem has claimed for a long time that JIT can get them to near native performance, particularly if you can, profile it and continually re-JIT. So a number of WebAssembly runtimes have an interpreter. All of them have an interpreter. A number of them have JIT compilers as well. Then there's ahead of time compilers, AOTs. And an AOT will, at the time it loads it, or it can even load off disk, a highly optimized version of the WebAssembly that's been compiled to the native architecture. So you might want to use that version when you're deploying something somewhere to a known target, and that known target is going to be responsible for executing that in perpetuity. Spin uses the AOT compiler. Fermyon Cloud uses the AOT compiler. So when I deployed that application, one of the things it was doing was AOT compiling it once it got it to the particular VM that's the worker node, or the VMs that are the worker nodes for that. So once you get to the AOT, then effectively you really are executing it at near native speed. Why not native speed? Well, the main reason is that there's still one performance hit you're going to take with WebAssembly, and it's a desirable feature. And that is that you've got a security sandbox that's preventing. So, okay, simplest, most trivial kind of call that binary makes to the system is to get the time or to get a random number, right? It's making a system call. So in Docker, that goes straight to the kernel, does the system call there. In WebAssembly, it gets mediated through WebAssembly's security sandbox. So literally, you can turn on and off these features. And that gives you a very high degree of control over the security environment. In that case, probably something that's probably always is safe to run, except in maybe some government-y circumstances. But other things like asking for a file on the file system, we might intercept that call on the host runtime and go out and load a virtual file system or load files out of memory or something like that, and never actually allow it into the system to even make low-level system calls. That'll introduce the sandbox basically introduces a performance layer. So you're going to get near native, but probably never what you would get running something unmediated by a sandbox, like say a raw C program. So our performance tuning testing has actually shown that that the interpreted one is quite slow, right? JIT it really depends on the runtime. Some runtimes have very sophisticated JITs. We use Wasm time, which is by the Bytecode Alliance. A lot of Mozilla developers, many of whom wrote the JIT layers for JavaScript for the SpiderMonkey. And so you get a fairly good JIT compiler in there. And then AOT, I think Wasm time has the best AOT compiler, and that's one of the reasons why we chose that too. So a little bit of a long-winded answer, but does that kind of get to the meat of what you're...
Yeah, I mean, I tried the ahead of time as well, and I still found that the performance difference was quite large, and I get that's what it's from, but to me, it's this claim that it's basically going to be the same, but then it's not, and so it's kind of like, are there going to be improvements that come?
Oh, yeah, I think there will. And also, you said Rust, right? Yeah, and so Rust is going to be, so you got some extreme cases, right? Rust and C and languages like that manage their own memory. You're particularly sensitive to these performance things. The JavaScript thing we saw earlier, it is possible that we could get JavaScript faster than native in the sense that when we don't have to load the interpreter and we don't have to load the files, we've just eliminated a bunch of slow I/O and startup time and stuff like that. So it's really partly dependent on languages, but I think you're right. For the lowest level system languages, the performance hit's going to be more noticeable than for .NET Stack applications, Python applications, things like that. I think it's going to go a lot faster. One of the cool things that happened in the Java ecosystem was that JIT compiling went through decades of iterations. And the improvements made from Java 1.0 to, even from Java 1.0 to about Java 1.6, when the JIT started to get really good, were like phenomenal. we're in the early days with WebAssembly. So I'm excited that I think as more people get involved in Wasm time and other low-level ones, and particularly people who have a history of performance optimizations, we'll see some really cool improvements there as well.